All right, so we have a presentation this evening. Our very own Mike Aimone, W-A-8-A-H-Z, is going to speak tonight about ham radio transmitters. He's going to be taking a look at how transmitters have evolved over the past 150 years in amateur radio, presenting data on how it all started, phenomenon that was considered a bane of interference generation, a spark of electricity. So, Mike, sounds very interesting. Over to you.
If you will, if this Ask the Elbra question was, tell me about the technological changes from crystal radios to the software-defined radios of today. By the way, the individual wasn't overly impressed when I pulled out the Shorewood reports and so look at this, what's happening in selectivity and selectivity and sensitivity. But be that as it may, we do know that there was an evolution in receivers. What was the revolution in transmitters? That's the question I have to myself. And so I went on a journey, and you're going to come on that journey with me. This is non-technical. If I get too geeky techo out there, I'm going to probably sink. So the first thing I did is I went to the club's journal. And I don't know if you're all aware, but the club wrote a journal in the 1990s called the Leading Edge. That's just a copy of one of them. I went out to the editions of the Leading Edge and said, gee, what did our forefounders write about transmitters? And I found out that they did a study of the founder called Loomis. Matthew Lewis was a dentist in Washington, D.C. His theory of atmospheric lightning said that I see lightning going from place A to place B, from cloud to earth, earth to cloud, but I also see lightning that travels from cloud to cloud. The atmosphere must be a conductive layer, and if it can conduct electricity, then it must be able to conduct telegraphy. And so in the 1850s, he put up a transmitter and a receiver. This 1850. He put up a transmitter and a receiver in the mountains of the Shenandoahs. In fact, the club celebrated his 100th anniversary with a special event station, 100th anniversary of that event. What did we call that, Lee? 150. And what did we call it? What was the special event station? Was K1T. We had a really nice venue for that, by the way. Colder than blazes, I might add. Well, I found out that another one of the Leading Edge documents talked about an inventor from Canada called Feinstein. And in fact, he was another one of the ham radio operators that we recently had a special event station. And Bill, you're here somewhere. What did we celebrate for the invention of Feinstein from Canada? So in about 1920-something, this inventor figured out how to hook up a microphone to what otherwise would have been a would otherwise have been a CW radio transmitter and get voice out the other end. By the way, his first couple attempts at that were disasters. He had to figure out how to mix the audio signal with the RF signal. Yes, he used something called amplitude modulation. But so I see that our Leading Edge authors talked about Nikola Tesla. And I think of Tesla from my electrical power days as the guy who was trying to use, let's get this right, he was trying to use the atmospheric electrical channels to transmit high power electricity from point A to point B instead of having wires. And he was doing that in the 1910s and 1920s. But he was an inventor of his own right and did a whole lot of things. So I went through the journals and I saw what was written there. I also went out to the club's presentation website. So the club lists and posts all the presentations that have, I guess, go back into the early 200s, 2020, 2010, 2005, something like that, period of time. So all the presentations, or many of the presentations, are there. So I found three of them that were helpful in formulating this examination of the history of radio transmitter technology. But I got to really build a little bit more on this. So we talked about Loomis in the 1850s, had a technology that he tried to do. He patented it. Frankly, technologically, it is not how radio waves work. But, hey, in 1850, that's what he thought. And he thought he could harness atmospheric lightning to produce wireless electrical communications. Well, Tesla was doing some of the same thing over again, but I don't think that in any of the work and writings of Tesla, he ever saw the work of Loomis. Well, but then there was a guy by Maxwell. By the 1860s, 65 in particular, he published a treatise, and this was the first unified theory. And this unified theory unified the effects of magnetism with the effects of electricity. And we think of those two things, magnets and electricity, as different. But as electromagnetic force experts, we know that there's a relationship between electric forces and magnetic forces. And in fact, Maxwell wrote a series of about 20 equations that described that relationship. Heaviside came about a little bit later. He was a telegrapher. He was just a non-educated guy that sat in a wired telegraph office and transmitted messages, frankly, from Sweden down to Denmark. And he was really curious because he was running some experiments. Well, he had free time sitting there in the telegrapher shack, where he noticed that the transmission in the underground water cable from Sweden to Denmark traveled faster than the equivalent guy sending a message going in the other direction. And he couldn't understand why the wired transmission was different going south versus north. And it turns out that he ran into the work of Maxwell. In the process, he refined it and reduced Maxwell's equations to 4. And that's what we all study, or at least the electrical engineering and physics community study today, is Maxwell's 4 equations. But that was actually the work of this non-college graduate practitioner who was trying to solve a dilemma that he thought was interesting. He wrote some serious papers on this and actually was inducted after some hoo-ha-ha into the Royal Society of Engineering in England. Marconi, towards the end of the 1800s. So we had Maxwell theory in the 1860s. We had Heaviside writing those equations in a frankly a more easier form to understand in the 1870s, 1880s. And Marconi shows up, another one of these guys who basically was an inventor. In fact, I would tell you he was the first amateur. And he took this work, and he took the work of Hertz, who was doing experimentation of essentially electromagnetic energy transmitting wirelessly from point A to point P. Marconi commercialized it. And we've all heard about the Titanic. That was a Marconi radio that broadcasted the SOSD. What does the D in SOSD stand for? Okay, CQD. Thank you. What does the CQD? What does the
Distress.
D mean? Distress. Hello, is anybody out there? I'm in distress. Okay, thank you. That's why this is interactive, right? Yell this stuff out at me. Marconi made this thing work. And DeForest was pretty interesting. He wrote somewhere like 300 different patents. He wasn't too concerned if somebody else had written the patent. And there were several patent fights. And in fact, DeForest ended up penniless at the end because basically people picked his patents, of course, and won in court patent infringement cases. But regardless, DeForest is credited with basically taking the Fleming diode, which was a 2-element vacuum tube, and make it into a 3-element vacuum tube. And that 3-element vacuum tube, that third element, a screen, could actually be used to take a small signal and make a bigger signal. And in fact, Armstrong came along about 10 years later and said, wait a minute, if I build a tuned circuit and provide positive feedback into that oscillator, the autoton that DeForest invented, triode as we know it today, I can make that amplifier, taking a small signal and making it a larger signal. I could do that and make it an oscillator. And oscillation is what makes transmitters work. So, okay. Then I said, I got to fill in the blanks here. So then I said, gee, I need to look at the history of ham radio because I've never really done this. I was really looking for a little timeline, and I couldn't find a nice little timeline, but I was able to steal this document walking through the history of ham radio. And really the big point I want to bring out are twofold. In the early 1900s, there were about 10,000 or so Americans who were called private operators. We didn't use the word at the time, amateur operators, but they were private stations. And they were experimenting stations. In fact, the FCC at the time, it wasn't called the Federal Communications, but the equivalent to that in the early 1900s, actually licensed them with a call sign that had X in it, X for experimentation. I already mentioned Fleming developed the diode, DeForest developed the triode. And interesting, this guy Featherstone, we already talked about him, and he created the amplitude modulated voice signal. But he was also the idea creator of the Alex Anderson alternator. And I'll talk a little bit about that in a minute or two. So now we need to continue with this. At the top of the screen, a little bit more on history. 1908 probably is the accredited date of when amateur radio kind of started. Okay. It's a fuzzy, slow start. What do they say in a restaurant? A soft start. But it grew, of course, from then into now. And the first amateur radio club was the Radio Club of America in 1909, excuse me. By this time, Marconi had taken his spark gap transmitter. He invented it and reinvented it and reinvented it at least 3 times between the late 1880s into the 1990s before he could get to a commercialized product that he finally sold primarily to the maritime community. Why? It's really tough to talk to ships on the sea if you're dragging a wire from Sweden to Denmark underwater. So wireless for ship maritime activity was really the only way that you could do this. And there was a market there. He created a company. He sold radio transmitters. He sold the service associated with handling the messages associated with radio transmitters. And that kicked off the commercial and maritime radio business. I'm going to move on to say, if I were to summarize my presentation on one slide, this is it. First radio transmitter was basically a spark gap. It was already alluded to. It was a very harmonically noisy device. It created noise all over the band, and it did that because it was what's called a damped wave. A damped wave, well, let me show you what a damped wave looks like. That's a damped wave over there on the top left-hand corner. I strike a drum or I strike a chord on a guitar, and that string vibrates or that drum head vibrates, but it actually starts loud and progressively gets softer until you hit it again. And then it has another strike on the drum, and all those damped waves create harmonics. And we're going to get into that a little bit. So spark gap was the first credited transmitter. The most practical version of that was called a rotary arc, meaning that I had a distributor cap, like in an automobile, running, say, 6 cylinders or 8 cylinders, hitting a spark every time it went around the distributor head. Well, that's what a rotary gap transmitter did. Well, what does that mean? Well, it got rid of some of the dampness, particularly if I sped up the rate of that distributor rotor going around the gap of the electrical circuit. it made it more like a continuous wave. But the Holy Grail, and they knew this from the studies and using Maxwell's equations and things like that, that they needed to move to something that was truly a continuous wave instead of damp wave. And we're going to talk a little bit about two different versions of that in the early 1900s up to their heyday, which was in about the 1920s. By that time, World War I had ended. The vacuum tube, which was a phenomenal military use in World War I for radio communications, became a little bit cheaper. The amateurs began to experiment with vacuum tubes in the 1920s, and frankly, it was all history after that time. And we moved into vacuum tubes. Vacuum tubes got us to solid-state electronics. And frankly, now everything we could do in an analog circuit, we can do in a digital circuit. Interesting, when we do it in a digital circuit, we create harmonics that we have to work on. We created harmonics in the analog circuits, too, that we had to resolve with passband filters and the like. And then ultimately, we've moved not only from analog signal processing, where we could put a voice print on a radio frequency carrier, but now we can do everything, both the audio version or the digital 1s and 0 version and the RF frequency synthesized using computers and electronic hardware. And that's kind of it. Those are the generations. So we're going to talk about each of these a little bit. But let me just pause here because, frankly, this was meant to be, if we started late, this could be a place where I stop, and then I'll just hit a couple of pictures to show you things. But let's just talk about this. Damp wave to steady state. Those are really the two technologies. But what else happened when we started understanding about both analog and digital signal processing? What else was a driver besides going from damped wave to continuous wave RF carriers? The carrier is what the information transmits on. And I'll give you the word: modulation emanations. What do I mean by modulation emanations?
That's imposing the audio on the CW.
Okay. That is obviously one way of modulating. That is to say, putting a voice print on a 14.2 kilohertz, a 14.2 megahertz signal is by modulating using a fundamental form of modulation called amplitude modulation. Okay, what's frequency modulation all about? Okay, Armstrong in the 1930s said, well, okay, there are some limitations for amplitude modulations. One is all that lightning noise that Loomis was excited about being able to use to conduct electricity through the clouds, the atmosphere, and be able to transmit electrical communications. Basically, Armstrong says, I don't like all that static that shows up on my radio signal. And so he invented something called frequency modulation. If amplitude modulation emphasizes the sine wave with a imprint of the voice signal, what does frequency modulation do?
Varies the frequency with the audio.
Very small variations of frequency with the modulation, and we call that the deviation. Are there any other type of formulation? Is that it? Is that all the modulation types, AM and FM? Okay, John said phase shift. And phase shift and frequency modulation are very related, by the way. But okay, I'll buy that. There is a whole plethora of modulation types that are tied to phase modulation as opposed to amplitude modulation. But effectively, what I'm doing is I'm changing the phase of the signal, which is like changing the frequency of the signal. Pulse modulation, okay, where I literally start putting 1s and 0s. Now I'm beginning to move into digital signal processing instead of analog signal processing. One way of doing these ones and zeros is by something called frequency shift keying. What's frequency shift keying mean? Frequency shift keying is I actually have two physical carrier frequencies that I have. I'll call one the stop bit, and I'll make the other one the mark bit. RTTY uses, at least old RTTY, uses FSK, frequency shift modulation, to be able to send pulses of ones and zeros. Okay. What about PSK? If FSK is frequency shift keying, what is PSK? Phase shift keying. Okay. Now, each of these have a capability of physically changing the carrier frequency to be able to handle this differentiation. And most of these are for digital modes, where effectively what you're talking about is a bit stream of zeros and ones. Okay, so, and I can make anything, a letter or a number, out of zeros and ones, as long as I have enough way of doing that. But the whole idea here is anything I can do, say, for example, with frequency shift keying, two discrete, very closely connected frequencies, but frequency one, frequency two, and my carrier literally is changing from frequency one to frequency two as I send my zeros and my ones. I could do the same thing by using something called the audio frequency shift keying. And that's really the modern way that FL Digi sends, for example, RTTY. They don't change frequencies. They have a single frequency. Remember, these frequencies were very, very close together. But instead, you're using a single frequency, and you're adding a 0 or 1 as an audio tone coming out of your computer sound card. Same thing, there is an audio phase shift keying. So what Lee is saying, because I know that everybody can't hear him on the VTC land, is that there are a whole gob of different modulation types. So what I want to leave the slide with is, sure, there was just damp wave and continuous wave, right? But the magic sauce that made radios become ever more effective, just like the superheterodyne was more effective than the direct conversion receiver, the way transmitters evolved technologically was not by changing the frequency method of a sine wave, but was in fact finding new and innovative ways of importing information on that sine wave. A sine wave of a single frequency, 14.2 megahertz, has no information. If I try to listen to that frequency, when I tune to the radio, modern radios, I won't hear a thing. But there is a noise associated with the 14.2. It's a signal, and we can see that signal above the noise level, okay, on an AM signal, for example, because the carrier is not suppressed. In sideband, which is a form of amplitude modulation, we suppress the carrier and one of the sidebands. So, by the way, who invented the sideband modulation technique? Was this the military doing this? Who did it? Who created the entire sideband phenomena that we're so used to today? Okay, so there was a patent by Bell Telephone in the early
With carriers, they could carry multiple conversations on a single wire.
Okay, so they were doing this for wired transmission, but we were doing it for wireless transmission. So why does single sideband sound quacky? So back in the 1920s, the amateur was saying this vacuum tube stuff is not ham radio. Ham radio in the heyday was Morse code and a spark gap. By the way, those amateurs that migrated to amplitude modulation signals by FCC rules, what's the bandwidth of an AM signal? 6 kilohertz, right? What's the allowed bandwidth of a single sideband station? 3 kilohertz, right? So by definition, just as Lee said, you can get more transmissions when you use sideband than when you do AM. Now, you lose a little bit of the comfortness associated with the signal quality, but certainly we hams know how to tune a sideband station to make it sound pretty lifelike. By the way, why did talk radio stay migrating down in the commercial AM band between 550 hertz and 1500 kilohertz, 550 kilohertz to 1500 kilohertz? Why did talk radio stay down there? And why did music move up to the FM band? 2 reasons why. Can you think about them? What were they?
One was the ease of tuning it in your car, because most people back in the early days before they had FM in cars used AM receivers in their car.
And what happened to the radio station when there was a lightning storm?
Big noise.
Big noise, right? And of course, if you put a FM signal in, you won't get that disturbance that, if you will, disturbs the amplitude modulation, but it doesn't change the frequency characteristics. So it's less prone to interference like lightning. But that's just one reason. Why the quality of FM better than the quality of AM in the commercial broadcast business? Bandwidth. So the typical bandwidth, as you add bandwidth, you add more quality. Let's just imagine for a moment that the gist of this conversation is, okay, damped wave and continuous wave, I get it. But what the big cheese over the last 25, 30 years has been a plethora of modulation emanation types, more than you can imagine, more than you may necessarily use yourself. But in fact, other parts of the ham radio community are using all the time. So the folks doing EME work have a modulation type that is fixed for them. Those doing weak signal stuff, WSJT type stuff, have a type of modulation and a equivalent decoding capability, not in the radio, but in the computer, that allows for a capability that would not necessarily be out there, a capability of picking up weak signals. So I want to leave this conversation with, what's the future then? If I've said, okay, people are continually inventing new modulation types for unique and specific cases, and I haven't even talked about modulation types and associated codes that go with those. Morse code is not a modulation type. Morse code is the dots and the dashes that translate into letters and sentences and paragraphs. It's done using continuous wave, and literally when key down, the continuous wave is sending. When the key is up, there's no sending. So it's the other way around, I guess. No, it's that way. When I press the key, I'm sending a signal. When I not press the key, the signal stops. Okay. And in fact, and indeed, I get a signal out of that. How do I get a signal out of that if I'm not modulating the continuous wave transmission? There is no modulation mixing going on inside that. That's exactly right. Don, you're right on. So we hear a signal in our receiver. If you were just a transmitter, you wouldn't hear anything coming out of the transmitter unless you have very fast rise times from what's called key clicks that can occur when an operator is really working hard the key or working it very fast. You can get key clicks. One more thing about CW I find is really interesting and educational. So if you send Morse code slowly, how much bandwidth do you use approximately in the amateur radio band? About 50 hertz. Okay. What happens if you speed up and send a message, a faster sending rate? What happens to the bandwidth? It increases. There's a law in electrical engineering called the Shannon law that basically says the more information you pack into the signal, the broader the bandwidth has to be. Hence, think about this. Why is our voice print 3,000 hertz, not 50 hertz or 65 or 70 hertz? Or with WSJT, I think it's 64 hertz. Okay. But why is it 3,000 hertz? So we can pick up the lows and the highs of our voice print. I need that bandwidth. Okay. What about future technologies? And if you allow me, these slides are up on the website in the presentation area. Take a look at them. If you do nothing else under the spark gap damped wave transmitter slide, that YouTube is about 12, 13 minutes long. It'll give you a really good discussion about everything that I was trying to say today. So take a look at that YouTube. Spark gap, one thing about spark gap I always kind of chuckle about is, what do you think that dark thing is above the batteries and above the telegrapher's key? What do you think that looks like? A coil. What kind of coil? How about a coil that's inside of an automobile? Okay, ignition coil. That's exactly what these guys did. What do you think that spark thing was? That's the automobile spark plug. This was being invented in the late 1800s. When did the internal combustion engine get created? 1860s, 1870s. These guys just stole from the automobile industry. That's where they got these things. Of course, after time, Marconi needed bigger stuff. He couldn't just get by with London jars to be his capacitor. In fact, over here in the top right-hand corner, he had whole halls of these metal plates. That was his capacitor bank. Marconi is that little guy in the red circle. I talked a little bit about early continuous wave, and I mentioned that Fedestein worked with a guy by the name of Alex Alexander from GE, who basically created an electric motor generator set that spun very fast. And the problem with generators, when they go really fast, they fly apart. So the idea was, how do I get to a reasonable transmitted frequency and not have the generator basically fall apart? And that was the invention that GE built. That created a true continuous wave transmitter, but all it was really a motor and a generator operating at a frequency, creating that continuous wave. Moving on a little bit, I'll skip over this. I'll skip over our modulation types. I didn't talk about spread spectrum. I would have done that, but I didn't do it, so I won't. I talked a little bit about modulation and CW, and Don's absolutely right. The sound you hear is an artificiality of the receiver, where you beat a frequency against the carrier, and that sets up the pleasant tone you use to copy Morse code with. We moved from spark gap to rotating machines to ultimately vacuum tubes. They could be done in the form of a vacuum tube circuit, or they could be done in solid state or integrated circuits. And I could talk a whole lecture about digital signal processing, but I won't, because I really want to get down to what's next. What do you think the next great invention of amateur radio transmitter is going to be? What did I hear over here? Telepathy. Okay, just mind sending signals. Well, I might argue, is that radio frequency? So what is radio? I mean, I went back and said, what is radio and what is radio frequency? And said, okay, maybe some of these things don't count. I could tell you that amateur radio still is in fact have authorization to work spread spectrum. We think that the big holy grail, right, is to have a signal that's above the noise level. In fact, we work really hard as hams to filter our signal down so that we reduce the noise associated with the signal so we can hear the signal. Now think about this a different way. Why do signals fade during the daytime? Maybe on 20 meters, or certainly at 10 meters. Why do the signals fade? Well, propagation, but what's driving the propagation? So the ionosphere is changing, right? But the ionosphere is getting noisy with the sun. Noise rises. Why is the 160 band the best in the middle of the night? No noise because of the sunlight impinging upon the ionosphere and other things, of course. Fred Spectrum totally changes this around. It says, let's just put this signal in and among the noise. But we're going to tell you where to go listen for this signal. And only you will have the secret decoding code of where to listen for it. In fact, spread spectrum was primarily a military thing for a long time. They were sending signals basically in the noise level. This was way before WSJT created FT8 and FT4. But what they did was they made it very, very broad. And then they gave you the code to decipher it. FCC doesn't like that because then you could start, this is effectively encrypting. And what also the military found out as a happenstance was the spread spectrum characteristics are less impacted by fading. Ever been on 40 meters and all of a sudden the signals just drop out in the middle of your QSO? Yeah, I've had that happen. Okay. Well, less so with spread spectrum. I think we'll see more of that. By the way, WSJT publishes their code so that others can look and see. Let's see. What else about internet radio? Bill, this goes back to your question. Was Spark Gap the only thing in town, and those people that created continuous wave, was that really amateur radio? Was AM really amateur radio? Was sideband really amateur radio? Was this WSJT FT8 really amateur radio? We have a history of being naysayers with regards to advanced technologies. What about internet radio? Is it radio? A little bit. Is it the internet? Yeah. DMR is becoming a international standard digital mobile radio tied to the internet. What about something called cognitive radio? We had a presenter a couple months ago talk about software-defined radios and GNU. Well, she also touched on cognitive radio. As Kevin said, in cell phones, there's a whole bunch of spread spectrum as frequency hopping capability. If cell tower number one, receiver number one is busy, I'll look and see what the best next place is. In fact, I can drive with my cell phone from here to Richmond and never get dropped in a phone call because the Fred spectrum capability of the cell phone is looking for always the strongest receiver transmitter pair to be able to talk to. By the way, that's how DMR works. Okay. It has a modulation emulation type that allows that to happen. Cognitive radio is kind of like this, but it basically says, where's the best signal and where can I go to get it? It is basically another application of spread spectrum, but it's thinking ahead of where I'm going, what I'm doing. It is thinking. That's where the cognitive part comes. And I'm going to change frequencies because I know that I need to be here to be able to do that. It's not in amateur radio yet, but it is beginning to show up in 5G. Optical communications, photonics is the technical term in universities today for optical science. It's outside of the RF range, but it certainly is electromagnetic waves. It doesn't do very well in the ionosphere. And, I'm kind of one of those guys that like to work the ionosphere. So I'll probably be stuck in my old age working HF and working RF signals. because I like to bounce my signals off the ionosphere. But that's not everybody's cup of tea. There's a whole lot of things coming out. And then the last one I put in there, I won't be around to see this, so I'm willing to put it on the chart. But what about quantum computing? It is, in fact, a thing. People are thinking about it. There's the theory in quantum mechanics. Somewhat of the theory is something called entanglement. If I have a particle over here, and if I have a particle halfway around the world or halfway out to the end of the cosmos, those two particles can be entangled. If I have a change of state in particle 1, it has a change in state of particle 2. It's simultaneous and, in fact, not behaves the rules of speed of light. Ooh, not there yet, but I'm willing to bet you, and there's, in fact, researchers in the university world looking at how can I employ quantum mechanics and quantum entanglement to create conversations, although they're mostly optical, fiber optics based. But I hope what I've left you today was we grew out of the telegrapher's world. Heaviside was a telegrapher who was trying to figure out why signals going south were different than signals going north. Using Maxwell's equations, he proved to himself that the magnetic fields of the Earth were affecting, and maybe of the magnosphere, but were affecting the signals as they transferred one direction or the other direction. We've had all of the great amateur radio operators had early great operators had a history in telegraphy, commercial telegraphy, including marine radio. Okay. We may be one of the last vestiges of continuous wave Morse code operations, but I don't think we'll be the last generation. I think quantum mechanics is something we should think about and watch as it develops, just as I think you'll see these advanced stages of software-defined radios become more effective than they even are today. So that was my presentation. My intent was to do a non-technical talk. I'm concluding that, well, maybe the gizmo didn't change much. Yes, continuous wave instead of damped wave reduced the humongous harmonics problem associated with the Marconi spark gap. But where the sauce was, the secret sauce was the invention of all kinds of modulation types best fitted for the mission that was being performed, be it EME, Earth to Moon to Earth, be it weak signal or the like. And I hope that's what I've left you with is modulation types and the associated codes that go with that is where the study should be. And I would hope that the program committee next year would pick up on this lecture and go into this discussion about modulation types and do some of the geeky technical stuff, because that's where our hobby is going.
Right. Thank you very much.